Hi. Thanks for the opportunity. This has been really fun so far, and looking forward to tomorrow as well. Right. So most of the talks have been about using ML for science, and I usually spend most of my time thinking about the other direction. As Arena mentioned, I like to think about how models behave as we scale them up, what problems are solved by scale alone and what are not. And today I'm going to talk about a collaborative benchmark that we put together to try to give some experimental data to investigate these questions, especially in large language models. And just to make sure for context, so I'm going to be talking about large language models, which for me means that we generate a huge training set, typically by like downloading the whole internet, and then we train models by giving them some sequence of text. Can we predict the next word that is going to appear? So we do this large scale pre-training, and then the evaluations are going to involve no additional fine tuning. So there's no fine tuning of this model, but we can prompt them in different ways. So for instance, we can prompt them so they get the flavor of what a answer to a question is supposed to look like, or something like that. But here are all the evaluations. There's no fine tuning involved. Okay, so. Right. So the goal of this benchmark is it's a living benchmark. Currently, it has over 200 tasks, and we put out a paper recently on the first version with over 400 authors. This looks funny, and especially to like a CS audience, but like coming from a high energy physics background, this is like a small paper for like the Atlas collaboration or whatever. So, right. So the goal is to try to measure the capabilities of current models and hopefully extrapolate their future capabilities. And so some background and motivation of where this is coming from. Well, we can look at what the loss curves look like as a function of model scale or compute as we train models at different sizes. And here I'm showing different language models, but you get the same qualitative behavior also in image domain. And what we see is a reasonable approximation to something that looks like power law improvement over many, many orders of magnitude. So we see something that just looks like systematic improvement on loss over a huge number of scales.
Ethan, can I have a quick question? So each line corresponds to a model, a particular model with number of parameters?
That's right. So each line, you're training a model for a different amount of time. And so the compute optimal point here is to sit at the kink where the model turns over for each model. So here the x-axis is compute. And so what you'd like the optimal training would be to sit at this kink for all models.
So this is Daniel's plot, but you only show two curves. Is that what it is? Okay.
And I should say, please interrupt me at any point with questions throughout the thing. Yeah, that's great.
Too late to work on that.
Yeah. Okay, good. Right. So as an aside, there's a lot of interesting work, and I'm happy to talk about it offline if people are interested, trying to theoretically explain these scaling laws. And there'll be some Cengiz, sorry if I'm mispronouncing or butchering your name, but has done some of this work. We've also worked on this some, and happy to talk about it more if people are interested. But that's not what I'm going to talk about now. So what I want to say is, so loss is very interesting, but usually with these models we care about how well do they do in some downstream task. We care about, and if we look at evaluations on those tasks, they also seem to, at least on average, exhibit similar behavior. So here's a plot taken from results in the GPT-3 paper where we look at performance on all the benchmarks that they evaluated on, and we see that there seems to be pretty systematic scaling there, and in a few orders of magnitude, these models will have broadly superhuman capabilities. Right. So now, why do we need a new benchmark? Well, a lot of the benchmarks that we have in natural language are broken or close to being broken. So here's a common benchmark called superglue, and it took about a year from the origination of this benchmark for models to achieve superhuman performance on it. How do we choose?
Yeah.
Maybe I'm not understanding the question. You mean like as a researcher, how do you pick which benchmark to evaluate on?
You say why a new benchmark,
Yeah.
right? But the question is, which should it be?
Well, here I'm using, I'm saying we have some number of publicly available evaluations that we can compare on, and why do we need to add another one to this list of many that already exist?
And
Yeah.
how do I make that choice? That's what.
Yeah, so you want, for instance, it's not that informative if you're already, if all the models are already saturating performance, doing perfect on this benchmark, then it's not a useful benchmark for getting gradation about how good your models are doing. Also, if here Big Bench is quite diverse in the types of questions it's asking. If you care about something, right, you should choose a benchmark that's related to the thing you care about. Hopefully, either there are some tasks here that are close to what you care about, or if not, you can add your task and it'll be evaluated on these big models. So just to say, there are clearly things, so I said a lot of these benchmarks are already beaten, by these models, but there are clear things these models can't do well. Here's an example from Big Bench. So here's a question where it's, there's an empty fruit basket, then one fig is added, then one plum is added, then one date is added, then one plum is removed, then one fig is removed, which fruits are in the basket, and the model says that question will get 71 views, but a related question about how long does it take to finish work would actually get over 1,500 views. So, which is not the correct answer to this question, but it does indicate the kind of data that these models were trained on. Okay, so right, so as I've now said a few times, the goal here is can we understand, can we have a broad set of tasks and understand which of these are solved by scale and which are not, and when we can expect broadly human capabilities. And so that's the reason for this benchmark, it's open call for tasks organized on GitHub. If you think there's no way these models will ever be able to do this favorite thing that I care about, I would love, if you want to add that as a task, like that's the whole goal is to have tasks that people are interested in and think are very difficult for these models. And so, okay, to give some of a flavor of things that are there, here's just 4 examples. So this Crash Blossoms task asks models to identify parts of speech for potentially ambiguous words. This code line description task asks models to understand code and describe what the code is going to evaluate to. The emoji movie tasks asks if models, given a sequence of emojis that describe a plot, can guess what movie it is. These tasks can be submitted either as JSON, multiple choice, generative tasks, or fully programmatic tasks. So this interactive 20 questions task takes multiple turns of interaction with the model. And tasks are labeled by keywords, so you can sort of get a sense for what kind of tasks are present in this benchmark already.
What is the y-axis here?
I guess the density, so the fraction of tasks that have this keyword.
Can you read some of the keywords?
Sure. So the first one's multiple choice, so maybe it should have just been cut. But logical reasoning so multiple choice, logical reasoning, common sense, reading comprehension, many shot, mathematics. The tail, okay, yeah. So conversational question answering, inclusion, context-free, semantic parsing, toxicity, morphology.
So what is the y-axis then?
This is the density. So this is a fraction.
Fraction of the tasks that have this characterization.
Yeah.
So what do we learn from this?
You learn, for instance, that there's like many logical reasoning tasks and not that many multilingual tasks.
It's able to look at. There's no. Yeah. Okay. But if you look different, then.
So one use of this is, for instance, you can like look at performance, like do these models do well on logical reasoning tasks, but do poorly on, yeah.
But that's not about doing well. That's
Sorry, you're asking like how much do I learn from looking at this histogram and asking about like what this histogram looks like? I mean, not much, I guess I mean, if you want to know, are there tasks that I care about, but.
But you chose them because you think logical reasoning is a weak point for GPT-3.
So, so I should say, like, we didn't choose them except to review them. I mean, we submitted some, but this, I think, many people thought logical reasoning is a weak point, right, so the purpose of this benchmark is to evaluate how models are doing, and so for this initial release, we evaluated this benchmark on a variety of models. So this includes some Google sparse and dense transformer models, and also OpenAI's GPT models. And we see that the aggregate performance on this benchmark, does seem to systematically improve with scale. Here we're evaluating these on models from 2 million to hundreds of billions of parameters. So this is an normalized aggregate performance. So for each task, the submitters define a low score and a high score on the task. So for instance, for multiple choice, the low score would be random performance and the high score would be 100%, but not all task metrics are multiple choice. So for instance, for like blue score, the max is 100 and the minimum is...
I think his question is, why is there 16, not 32?
Yeah, so sorry. And so for each task, we normalize using this high and low score and average, and normalize by 100. So perfect, high score would be 100, and this is getting.
So this is good or bad?
So if we compare this to how human evaluators do, then so here are human baselines. So the light blue line is we collected human results on this benchmark. And we see that the current models are performing far below the human evaluators, the average human evaluators, and very far below the best human evaluators in this test. The task line is the best rater. So we have this pool of human raters, and we take the best rater for each task, and that's their performance. Mm-hmm.
The projection is that you have to be 10 to the 20s or 100.
That's the naive projection of this.
How many synapses do we have? I feel better.
So
Microphone, because he's vaping it. You should use the microphone because he's vaping it, otherwise.
Yes.
yeah, should I continue or?
Yes, please.
Okay.
For one more minute.
One more minute. Okay. So, all right. So there's a question about, so this aggregate performance looks fairly systematic. There's a question of, can we predict performance on particular tasks? And I'll try to go quick, but I would say that some tasks follow this and just improve systematically with scale. So here's an example where models are asked to translate, and we see this systematic improvement. Some, on the other hand, show no improvement with scale, and some show this sort of interesting breakthrough behavior where at some critical scale they all of a sudden turn on. So this predictable behavior can depend on some brittleness of the model, but maybe given lack of time, I'll just say that one goal is to be able to predict and extrapolate the capabilities of these models, and this fact that some of these models only show any sign of performance gain at some critical scale is begging to be understood. So okay. So maybe just briefly, like we want to understand where these models will be. An ultimate goal might be to make an AI scientist to solve problems. I definitely don't think we're there yet, but here's just an example of the types of things these models can do at the moment. So here's a question, and here's an output from one of these models. And so definitely, we're not at the level where these are AI scientists, but there definitely seem to be like reasonable AI students. Thanks for letting me ramble at you. So in summary, there's this big benchmark, which if you have some question about these big models, there might already be a task in there that gets at what you're interested in. If not, please contribute. Some elements of model performance are very predictable and follow systematic trends, and others don't and are begging to be understood. And as a shameless plug, we're having a winter conference at Aspen this year on physics approaches to understanding deep learning. So I'd encourage everybody to visit the website and apply. And another shameless plug is, being an industry, we're sort of we work on this scale frontier, big models trained on lots of data, and it would be great if there was also, if these things weren't siloed behind industry walls. And so this, we were asked at the beginning, like, what should the NSF be thinking about, things like that. I think it would be awesome if there was more public, big science efforts, collaborations towards studying the scale frontier. So, yeah.
Thank you very much.
Here they have all money in the business because their conference in the winter in Aspen, not December.
That's a physics series.
So, so I have a question. So, let's say that you go to a university and then someone forces you to take every single course in the university.
Yeah.
You would do very poorly on most of them. Now, let us imagine that there is a copy of 25 students, all very smart ones, who take 25 disjoint sets of courses. They would all do pretty fine on them. So when we create these benchmarks, it seems clear to me that one big model trained on all these tasks would never ever hope to do well on all of them.
Why?
Or rather, like, if the model does well on all of them, then it got to basically solve each of them independently. What makes us I don't know. I don't understand the utility of clubbing together very diverse tasks.
So, I think it, especially because it's difficult to retrain these models, if we can have like one model that can solve all of these things, it's like better than having to train, a new many billion parameter model for each of them. Also, it seems clear that there is, at least to some degree, transfer between tasks in these models. So, you can take a model that's trained on the internet but without much mathematical content, for instance, but like with lots of stories, and then further train it on web pages that have math, and then ask it to tell stories about mathematical topics, and it'll sort of combine these things. So at least to some degree, there is transfer between different tasks that these are trained on.
There'll be some transfer, but not good transfer. It's like a student of physics and then putting him in a biology class.
I think there's no reason to think that these models are like one human. Why not two humans or seven humans?
So I appreciate that. I wanted to know how you think about this. This is a question that seems very paradoxical to me.
Yeah, I think this is. I'm sure I'm naive about how I think about it, but they definitely don't seem like a single cohesive personality. You can, for instance, prompt them and they'll sound like Wikipedia, or prompt them and they'll sound like a Reddit troll, or so they definitely can be elicited to respond in lots of ways. So I think they're like representative of the distribution of voices that you hear on the internet, rather than being like, oh, I've trained it to be like this one, something we would view as one cohesive person or something like that.
When you're hearing your own voices, yeah.
You just show that if you increase the number of parameters, you have an improvement, right? A consistent improvement.
On average.
On average. Did you guys also do the same thing about the training data?
So not in these plots. On the cross entropy curves, yes, you've done this in
So
data
do you
and
always
parameters
get
compute.
because what I was thinking is typically a human will not have the whole internet as a training set, right?
Right.
So I'm guessing you don't need the whole internet.
I think. Well, there are a few. I don't know the best way to think about this. These models just get better in a predictable way with more and more data.
Okay.
And they are fair. Like, this pre-training stage is quite data hungry if you want to compare it to like a human learning from childhood or something like that. Although I don't think we have great ways of quantifying like how many words is every second of what you're seeing or something like that.
Okay, but you do see also a consistent trend
Yes, yeah,
upwards
you do.
with more data.
Right. I also think it might be appropriate to compare this to like all the data in evolutionary history rather than just a lifetime. Like, you know, we're taking these models from nothing to something. Like once you're done with this pre-training, they can learn with many fewer examples. So,
May I ask a provocative question?
of course.
So, given the scale and how many exaflops that takes, so there's probably like 3 to 5 places where you can, in the world, where you can train those models. So don't you think that this brute force approach is maybe not the right way to go? For example, if NSF would provide scientists that amount of compute, we can solve many of the problems with direct physics-based simulations.
So the amount of compute that is used to train these models, certainly if you wanted to just naively extrapolate and like train the model that's going to solve all of these problems, that's like not a realistic amount. But these biggest models that I'm evaluating, you know, you could, if you were allowed to use like all of NSF, you know, some NSF cluster for some amount of time, it's, you know, these are not, these are tens of millions of dollars in public compute pricings, not billions of dollars in public compute.
Yeah, but typical scale of this, tens of thousands of GPUs or a bunch of TPU pods for weeks.
Yeah, so here we can.
That's a lot of compute.
It's certainly expensive. It's less expensive than, you know, it's orders of magnitude less expensive than like the Apollo mission or Manhattan Project or it's you know, it's less than but somewhat comparable to like LHC or other large public science efforts.
Just to say something. But humans learn in context. We use context. There is no context in these machines.
How do you mean?
Well, I know what meaning is. If I read a text, I can expect what's the next word just by the meaning, not randomly guessing what the word's gonna be.
If I've read the first 10 pages of a book,
Yes.
then I've used that to develop context, then I can have better chance of predicting the next page, which these models are able to take advantage of.
But they don't have meaning. They don't understand meaning.
I'm
They don't
not
understand
sure
what
that
they're
that's a
reading. They don't understand what they're reading. Right?
Is that a well-defined statement?
Yes. He's still a talking though. What's the context of your statement?
Let me say, interesting talk, and I appreciate the effort you're making to introduce metrics because they're very much needed in the NLP community. I was going to rephrase Alexander's question. I worry about how much energy these models are using. Google can foot the bill, and I couldn't care less about it, but what's the negative impact? From what I read from these models, if I get a 1% improvement, all right, but what is that costing me? How much CO2 emissions? How much energy? Is there any thinking at Google about constraining these models? You got an earlier question that, well, if I take 25 courses, I will do badly. Thing is that your brain is increasing here. Humans don't go this way because then, we are energy constrained. So is there any thinking along these terms?
Yeah, there's definitely a lot of discussion about this, and I think there's some. Certainly, I'm not head of this policy and take what I say with large grain of salt. There's I think thinking at lots of different levels. There's all of this is offset. Not that you necessarily should believe that these offsets are very meaningful, but 100% of the compute cost is offset. I forget the deadline, but Google is switching to being 100% renewable based. I think there's, I am it's interpreting your question broadly. It's not just what's the carbon footprint, but should we really be just continuing is this the right way to do science, to continue to train these big models over and over again? And I hope the answer to that is no. In some ways, these big models trained on the whole internet are much more reusable than models that I've trained on some small slice of data. So a given big model that we train is then used on like, for all sorts of studies and small amounts of fine tuning and stuff like that. So that helps amortize the cost a bit. I guess when I'm when I'm advocating for public version of this, I guess, one example is these breakthrough phenomena, but these models often just exhibit qualitatively different behavior than sort of models I can train on a workstation with a, single GPU or even, a few GPUs. And so I think there's I think even just having, one of these at each, I don't know what frequency, but every 4 years train a model sort of at the scale frontier is a good way of keeping science honest, studying these models, keeping what you're doing honest about connecting with the, the features that emerge at these big scales.
But your brain uses 30 watts. It's much easier, much cheaper. And you eat food. And anyway, let's move to the next talk, and we have a discussion after that.